I don't really. Should I just start?
Yeah, go ahead.
Okay, so hey guys, I'm Alice, and I'm a senior engineering physics major, and I'm actually doing the material science BSMS, which is why I'm in 428 and not in 328. But I wanted to talk a little bit more about a theoretical aspect of material science, this X-ray absorption fine structure spectroscopy thing, or XAFS. What just happened? Or XAFS spectroscopy. And so throughout the presentation, I'm going to be referring to it as XAFS. A little bit of motivation and background. XAFS is a tool that is used to determine the three-dimensional atomic structure from experimental data. And I'll talk about the experiment a little bit more on the next slide. In terms of the method itself, it's pretty well established, but with our current computational power, a lot of its uses are relatively new. And Lewandowski's even brought this up in class several times with modeling of materials, stating that the increasing computational power is going to allow us to perform experiments, in computers that are simply not time feasible or money feasible to do in real life. And just as an added bonus for myself, it combines three of my most favorite subjects. And down here, you could see, I'll point with my mouse. Down here, you could see these are some structures I've been working with and some structures other people have been working with, and this is an equation that we'll be coming back to later. But a little bit more about experiment. Here, you could see a block diagram of the experiment. The X-ray comes down from the top right here, and it passes through a sample in a sample holder. As we vary the X-ray energy by changing its frequency, we get this graph. We get this pattern in our data. And here, the absorption is simply measured by taking the natural log of the initial intensity over the final intensity. And actually, in this data, these wiggles are what we're more interested in. And these wiggles are described by the XAFS equation, which we'll come back to later. But first, as we try to understand the data, I wanted to talk a little bit about basic physics. The X-ray here comes in and knocks out a core electron. To see this better, let's take, what? Oh, so this photoelectron spreads out as a wave, and all these waves interfere, like such. To see this better, let's take out the outer layer of atoms. So it's a mess, but essentially where the waves constructively interfere is where we have a higher probability of finding the electron, and where the waves destructively interfere is where we have a lower probability of finding the electron. And if we vary this so the atomic distance is exactly half of a photoelectron wavelength, we get constructive interference at the core atom. So this leads to a higher probability of finding the core electron back at the center atom, meaning that it's more likely to be absorbed back, re-emitting a wave of light that could be picked up by our detector at the end. So now we actually have all the theoretical tools to understand this equation. But so depending on how I do on time, we may or may not be able to talk about all the terms, but let's derive this equation. So coming back to this slide, constructive interference happens when 2 times the distance between atoms is equal to some multiple times the photoelectron wavelength. And since the wave is sinusoidal, our interference pattern should be as well. This gives us our first part in the XAFS equation, this sign factor. This sign factor. And since chi should be max when d is 0, it would be a cosine. A little sidetrack about these notes. I'm going to be putting our previous equation on the top left here and the final equation after accounting for whatever we discussed on the bottom left. And here on the bottom right, you could see the full equation, so you could kind of keep track of which terms we've covered and where we've been. This PowerPoint is freaking out on me right now. And so from the probabilistic nature of quantum mechanics, we know that as the photoelectron comes in, it may pass right through the green atom, or it could bounce off and emit this green wave. So this introduces a probability factor, f of k, into our equation. Now, for any given core scattering atom, the atom is going to have multiple neighbors. Also, the photoelectron might bounce off several atoms, returning to the core atom. So we have to sum over all the paths. And because of this, we have to redefine d to be half the path length. As you should be able to see, this could get computationally intense fast. But it's not all bad news. Because of a term that we're going to introduce later, we actually only have to take into account the nearest neighbors. And to make our computational load a little bit smaller, we introduce a degeneracy factor, so we only have to calculate the value for the same path once. And so, for example, in this example, the green path and the purple path here would just be clumped to be a degeneracy factor of 2. And because of this, all of this, the sum over I actually represents the sum over paths. Okay, we're getting there. In the real world, atoms are not stationary. They jiggle around in one place. So since this side atom here is jiggling around, when the photoelectron comes in, it can emit as the green wave or the red wave. And so this introduces a phase shift. And as you can imagine, the heavier the atom is, the less it wiggles around. So this is a factor of atomic number. Now, since we have a phase shift and a cosine is essentially just a phase shifted sign, we switch the cosine for a sine just for convention. Okay, so here's the deal. I've been lying to you this entire time. The more physics-oriented folks in this room might have picked it up, but a simple cosine of d function only describes a plane wave. To get a spherical wave, we just have to introduce a 1 over kd squared factor. We're almost there. The other terms are actually fairly straightforward, and one of the terms, the one to deal with multiple neighbors, makes our fit really easier, that I've mentioned earlier. So, first, some reduction factors. These factors come in two types, a path-dependent factor, lambda of k, and a path-independent factor, s naught squared. Because of this lambda of k and this exponential decay as a function of lambda of k, this allows us to ignore path lengths greater than a certain cutoff distance. And just as the path independency and time independency actually is the same thing, since the longer the path, the more time that the electron has to travel around to get back to the core atom. And next slide. So this is our last factor, and I've made it. What is this factor? Oh, right. So this is an averaging factor, and it introduces a broadening term. Since we're summing or averaging over all the atoms. And so I honestly don't really understand that much about this term, but it introduces a sigma squared here, which in Gaussian, well, I guess Gaussian calculus, it kind of broadens the peaks for us in our final chi of k data. So there you have it, the entire equation. And how do you get structural data from this? Well, glad you asked. So here's the final plan, and this is the last slide. We measure chi of k experimentally, and all we have to do is curve fit for d sub I values. Or alternatively, you could just take the Fourier transform of k-space data. And actually, the two methods, I'm using both of them for my senior project and my material science bachelor's. Oh, okay, PowerPoint's freaking out. I'm using both the methods for my project. And my project essentially wants to compare the two methods for certain materials. And yeah, that's it. Acknowledgements. Professor French and Estioli has helped me a lot. Kahneman has helped me with code. Department of Physics taught me all the physics. And these two people helped, well, one helped with data collection, and I'm currently working with some of David's code to model the materials, and then source for funding and references. Questions? You want to come up here, Jonah?
Yep.
Hello.
All right, questions.
I know I went fast. I'm sorry. Yeah.
No, you're fine. You made out of time. Jessica.
So my question is about is there like do you have so the original what is the name of the first slide, like the very first slide?
XAFS?
Yeah.
XAFS?
So,
X-ray
so,
function?
yeah. So I'm just curious, like, does that are there quantifiable, like, do you graph these averaging factors, or how do they tell you, like, how does you get information? Like, what
Yeah, whoa, okay. So this entire thing is your XAFS data.
Right.
And what do you mean? So this is actually the chi of k equation fit.
Right, so that's permittivity, right?
No, the chi is an absorption factor.
Okay. Thank you.
Cool. Jenna?
So are those the only materials you've kind of tested with this, or are there other ones?
Yeah, so the materials that I'm trying to work with at least are glasses made from cobalt, nickel, titanium, and niobium. And I've only been able to start doing the crystalline solids for now, but eventually I want to like mix glasses and get different concentrations of these metallic glasses.
Chuck?
Yeah, at the beginning. Oh, it's actually right here.
Yeah.
The X-ray energy, and then like
This?
the
This?
absorption.
This one? Oh, okay.
Yeah. Since like the I going in is like
The I
less
going
than
in.
1, or it's like at the beginning. Does that mean?
Oh, like the pre-edge, like
versus,
this
fluorescent,
point?
Since like the outgoing.
Oh,
absorption.
so yeah, to understand like this full graph, it's actually so these X-rays as they're coming in, they're a function of energy. Oh, they're a function of the X-ray frequency. So before it hits a certain energy, it doesn't interact with the material that much. So it essentially just passes right through.
Maria?
And then, you know what okay. Sure.
I just wanted to know more about the geometry factor that you're talking about, the spherical wave.
Oh, okay. Mm-hmm.
Why is it 1 over k d squared instead of the black box
I think it's something to do with quantum mechanics. I actually have like an entire, hang on, if I could find it, an entire theory here. So I think like if you calculate the psi of kr, psi being the wave function, and if it's a spherical wave and you solve Schrodinger's equation for it, that's what pops out. I think that's mostly where the kd squared came from.
Okay, any more questions? Cool. Beth?
You mentioned that the probability of finding an electron, like reference to that
Mm-hmm.
diagram,
Yes, yeah.
was depending on either constructive or destructive
Mm-hmm.
waves crossed. So how did you factor that into the entirety of the equation? And also, does that diagram like show you the constructive versus destructive, or is that just in general?
Oh, okay, so yeah, the constructive is where waves. Oh, this is essentially only like a diagram, but constructive interference happens when like wave fronts meet, and destructive. So also this is a really bad diagram. I'm just starting to realize. But so if you think of plane waves, constructive interference happens when the wave fronts, like the peaks line up with peaks and troughs line up with troughs. And destructive interference happens when the peaks line up with the troughs. And so the way like this relates to the equation would be through, it's more through the center atom because of that like distance term. And so if it constructively interferes at the core atom, then the probability there is higher. And if it destructively interferes at the core atom, the probability of it coming back is lower, and so the electron is essentially like lost to the material, and it doesn't come back.
Ben?
I got a little bit lost because it looks like you're trying to get the properties of crystal structure, while later you told that you're working with glasses.
Yeah, so this equation works with any type of material, like any structural material, which is actually why we're using XAFS instead of some other like more conventional X-ray diffraction techniques. I could only measure like the distance between certain planes in a crystalline structure.
So in here you're
I'm
doing
outside.
atomography of it, or?
Yeah, so with this structure, for example, in the glasses that I showed way back, so in this slide, you could actually physically measure, after you measure chi of k, you could fit for the R values. And so you could find the distance between like individual atoms in here. And that's how you get the structure out.
So is it a surface technique, or you're passing the beam through?
It's, yeah, well, you could do it in either way, but we're mostly passing just the beam right through. Our samples are like 10 microns thick, roughly, so it's not too thick, and the beam just goes through.
We're out of time for questions, so I can't do any more. That's all I have today. Yeah, I'm done. My instructions say 5 minutes per presentation for questions. All right. David's asking a question. Okay.
You said you wanted to look at
Oh.
glasses.
Okay.
So how do you expect the amorphous structure
My
to
points.
be like different than the? Because you have a lot of crystalline structures here,
Mm-hmm.
and you showed like regularity is what causes the ability for you to image it. So how do you expect the amorphous structure of a glass to actually impact your ability to measure it?
I don't think it does that much. What do you?
But you were showing like the regularity and the
Like, what's like?
yeah, constructive and destructive interference of the atoms.
Mm-hmm.
But that would be harder to like quantify in amorphous, wouldn't it?
Yeah, well, okay. Yes, but also what we're measuring here is like the distance between two individual atoms. So at the end of the day, after we sum our data and like essentially take the Fourier transform and get or fit the equation and get this, like this big peak here corresponds to the nearest neighbor distance.
And
So
are you expecting to see a sharp peak like that in an amorphous, or would you expect it to be, because it wouldn't be as regular, is what I'm trying to say.
I honestly don't know what I'm expecting for amorphous. I think there is going to be a sharp peak, just because, like, for example, whoa, okay, PowerPoint stop. Just for example, if we're dealing with, like, say, only nickel and cobalt, there's going to be, like, a distance that the nickel atoms want to hang out with the cobalt atoms. But, so locally, we could actually have, like, pseudocrystalline structures in this giant glass material, if you know what I'm talking
Rob.
So when you had the picture for constructive and destructive waves,
Mhm.
you had the one electron surrounded by it's like 6 or so.
Yeah.
If you were looking at yeah.
Mhm.
Yeah. So if you had more electrons present or less electrons present, would that change your equation because it would change the number of constructive and destructive waves going through it, or is the equation independent of electrons present?
I think I'm pretty sure it's independent, because when your X-ray comes in as a photon, it knocks out the core electron and
Okay, so
whatever
it's
that,
a
yeah,
factor around it.
yeah.
Cool. Are there any more questions? Cool.